So let's finish up by looking at section 5.1, which is on what we call exponential functions. So first thing we'll do is we're going to take a look at two different expressions. One of them is a polynomial. The other one is an exponential. Each one of those expressions has two things in it, an x and a 2. Does anybody remember what you call the thing that's lower than something that's higher? What do you call the thing that's lower? You have something higher, like 2, then you have the x that's lower. What do you call the thing that's lower?
A constant.
No, that's not a constant. First, that's a variable because it's a letter, but it's not the word I'm thinking of for that. Yep.
Coefficient.
A coefficient is when you have a number like in front of a letter. So like 4 is the coefficient there. Does anybody know? Well, how about the number that's higher then? That's the exponent. So the one on the left, the exponent is a 2, and the one on the right, the exponent is an x. So what do you call the thing that's below the exponent? Yeah.
Would it be base?
The base. Yeah. So that's the base. So in each one of those, they have a base and they have an exponent. The difference between them is, in one of them, the base is a constant. That's this one on the right. It's a 2. And on the other one, the base is a variable. Well, the one on the left, this is a polynomial. If you think about like y equals x squared, if you were to graph it, it would look like a parabola. And the reason it's a polynomial is because the base is the variable, and the exponent is a number that's not a decimal, and it's positive. Polynomials always have numbers here that are positive and not decimals. Like x cubed, 5x to the 10th, something like that. The one on the right is very different. It has a variable in the exponent. And when you put a variable in the exponent, it can make an equation a lot harder to solve. This one, not too hard to solve. 2 to what power would give you 8? Yeah? 3. The reason that one was pretty simple is because 8 is a power of 2. But if I said 2 to what power gives you 10, well, it's not 3, because 2 to the 3rd power is 8. And it's not 4, because 2 to the 4th power is 16. So now we get a little problem. It's a decimal. So that's a little harder to figure out, but we'll talk about that. So let me just summarize what I just said about which one was a polynomial and which one was an exponential. So when you put a variable in the base and you have an exponent that is not negative and it's not a decimal, it's an integer, that's a polynomial. 3x squared plus 2x. There's a polynomial. 8y cubed. There's a polynomial. Variable in the base. And the exponent is a number that's not negative and it's not a decimal. We've studied those a lot. Okay, we started talking about polynomials back in chapter 2 when we did quadratics. What we're going to focus on now are exponential functions. In order for something to be an exponential function, a couple things. First of all, the base has to be a positive number, but it can't be 1. We'll talk in a minute why can't it be 1. But it has to be a number that's positive and not 1. The other thing is you have to have a variable in the exponent. You have to have a variable in the exponent. those two things happen, then you have an exponential function. Now, I said that the base can't be 1. Let's see why not. Well, let's look at what happened if the base was 1. What would happen if you start plugging numbers in for x and the base was 1? Lauren?
The answer would always be 1.
The answer would always be 1. Well, if the answer always equals 1, like if you graph y equals 1, that's the horizontal line at 1. So this isn't exponential. When you're going to see, when we draw an exponential function, it should curve up very quickly. If it's always equal to 1, that's just flat. It could also curve down very quickly. One of these is exponential growth. The other one is exponential decay. We'll talk about both. So let's graph an exponential. I kind of just drew one for you, but let me do it on the calculator. 2 to the x. The calculator does a very good job drawing exponentials. We saw that sometimes it has trouble with certain things. Usually exponentials are pretty good. All right, so you can see it's kind of flat for a while, and then all of a sudden it starts to go up. What do you think the domain is for that graph? Yeah?
All real numbers.
It is all real numbers. It's going to go left forever. It's just going to basically look almost flat, but not quite never being completely flat. And it's going to keep curving to the right forever. So the domain is all real numbers. Every exponential function has a domain of all real numbers. How about the range? Does it look like this graph goes, let's start with up forever. Yeah, it does go up forever. How about down? No, it doesn't go down forever. It levels off, and it gets closer and closer to a value, but it never reaches it. What value do you think it's getting closer to, but never reaching?
0.
0. We can check that if we go to the table. And plug in some numbers that go to the left. Try like -5. It's 0.031. Do -20. -20 is scientific notation, 0.000009. So that means there's 7 zeros and then a 9. So it's extremely close to 0, but it's not 0. And as you plug in numbers that go to the right, notice how much it's going up. By the time x is 10, we're already at 1024. So it's kind of how an exponential looks. Curves up very quickly. Let's write down the domain and range. So domain, I didn't write the range, but that's okay. Domain is all real numbers. And the range we did for the last one was 0 to infinity. You can change the range. You can change it. How do you think you could change what the range is? What do you think what's something you could do? Yep.
Vertical shift.
Yep, a vertical shift. If you shifted it up or down, you could change the range. And when you shift something, is that a plus or minus, or is that a multiply?
Plus minus.
Plus minus. So if I put a +4 on the end, just like we did with every other function we've studied all year, +4 on the end is a vertical shift of 4. So now you just change the range. It's no longer from 0 to infinity. It's from 4 to infinity. How about the domain? Do you think you can change that?
No.
No. Domain goes forever left and right. If you shift something that goes forever left and right to the right 3 units, it doesn't matter. It still goes left and right forever. Yep.
The sentence below the domain, is that just a statement of like a condition of exponential functions, or is that statement of the rate?
It's applying to A, which is a condition about the base.
Okay.
It's a condition we already said. A is a positive real number,
Yeah, okay. So it's weird that it's not referring to.
but it can't equal 1. Okay, these are all examples of exponential functions. If you're not sure why any of them are exponentials, just ask me. But in general, they all have a base that's positive, and none of the bases there are 1. And they all have variables as exponents. Those are examples of non-exponential functions. To be exponential, you have to have a variable in the exponent. None of those have variables in the exponent. None of them. Any questions on why the top ones are exponential and the bottom ones are not? Yes.
Could the last one be an exponential function if you switch like the 2 and the x? Like, are we gonna get to complex ones like that where it could be like the 2 with the x is the exponential? If you just flip those 2, would that be considered one?
No, it would be, I don't know what that would be. It wouldn't be exponential.
Okay.
Because she's saying if you did this,
Yeah.
well, now you have something with a variable in it. If it was just the bottom part, sure, that'd be fine. Because that would just be a vertical shift up 3. But this top part, making it a fraction, that kind of complicates it. So, no. Yes?
Can the base be a decimal?
The base can be any positive real number you want, except 1. So the answer is yes. And in fact, when the base is a decimal, like 0.5 or 0.3 or something like that, we're going to see a different kind of curve than when it's bigger than 1. So whether the base is bigger than 1 or smaller than 1 kind of controls whether it curves up or curves down.
Is the domain for an exponential always all real numbers?
Yes. Yep. That's why I said this would not be considered exponential if you switch this, because the domain of a square root isn't all real numbers. It's only positives, so it wouldn't be exponential. Well, I should say the domain of a square root function is non-negatives. It includes 0, which isn't positive. All right, let's look at the difference between these two. They're both going to be exponential curves that go up. But which one do you think is going to go up quicker? Yes?
Would it be 3?
Yeah, the 3 to the x. Think about if you raise 3 to the 5th power compared to raising 2 to the 5th power. Well, 2 to the 5th power is 32. 3 to the 5th power, I don't even know what that is. 243, right? So the 3 is going up a lot quicker than the 2. Let's look at it. So 3 to the x. Let me get rid of that plus 4. Just want to look at it without that. So they're both going to look like they're on top of each other on the left. Because they're so close we can't even tell. But as you head to the right, you'll start to see that the 3 to the x does curve up quicker. And if you did like 4 to the x and 5 to the x, those would curve up even quicker inside the red line. But you still have the same basic shape. Okay, so if we're given something that has a negative exponent, in general, we don't want to deal with negative exponents. Right? We want to get rid of them. So anytime you have something to the -1 power, -1 basically just means to flip it. So like 5 to the -1 is 1 over 5. 5 to the negative 2 would be 1 over 5 squared. So what I want to do is I want to use this to figure out how we could rewrite something that looks like it's exponential, but it has a negative in this exponent, which kind of messes it up. We don't want to deal with negatives in that exponent. So I'm going to show you how to get rid of the negative. You know what? Let me do this on a different page. We have a to the negative x. There's a number that's in front of that x, even though it's not written there. What number is technically in front of it when you put negative in front of x? Yep. Well, yeah, it's like having a negative 1. So a to the negative x really means this. It means negative 1 times x. Now, look at what I just wrote down. I multiplied two numbers together, or two things together. They're not numbers. There's a rule from Algebra 1 for when you multiply two things together in the exponent. Does anybody remember? Like there's a rule, like this is an example when you add them. When you multiply things with the same base, you add the exponents. Well, we're not adding two things here, we're multiplying. So does anybody remember when you multiply two exponents together? When do you multiply two exponents together? Yep.
Is it when you're squaring something? Or you're putting an exponent to an exponent?
Yes, exponent to an exponent. Like if you had 3 squared to the 5th, that's 3 to the 10th. 3 squared to the 5th. You multiply these two together. So the only way, and actually if I write it this way, it might even be clearer. The only way you could end up with two things multiplied together is if originally it was a power raised to another power. That's how you'd end up with multiplication. So let's apply that right here. This must have been a to the negative 1 to the x. It's a power to a power. It's the only way you would have multiplied them together. And we just said what a to the negative 1 is. What's another way to write a to the negative 1 power?
1 over a.
Yep, go ahead.
1 over a.
1 over a. There we go. So this equals that.
So that's just the answer. You don't have to do
Yep.
anything after it.
Yeah, that's how you can get rid of a negative in the exponent. Essentially what ends up happening, you take the a and you flip it, and then you make the x positive. Okay, so from now on, that's how I'll do it. I'm just going to take the a, I'll flip it, and then I'll just make the x positive. And the reason why that works is these two steps in the middle that I just showed you. Okay, but I'm not going to do those two steps every time. Any question on how we got rid of this negative?
So why are we flipping it?
Why are we flipping it?
Yeah.
Because whenever you raise something to the negative 1 power, we know that it means to flip it from algebra 1. That's the definition of a negative exponent. It means to put it in the bottom. And that's the same thing we just did. So you don't even have to copy this part down. We just did that on the other page. Alright, let's look at this.
Quick question. So if it's like, since it's negative 1, why if it's like negative like 4? Did you still do the same thing?
Well, we're going to do it right now with a 2. So let's see what happens. We're going to have an actual number there, and I'll show you what happens. The top one is fine. Now, the bottom one, when we look at it, you might think that the base is a 2. And I guess the way it is written, it does look like the base is a 2. But the problem is you have a negative in the x. Using the formula we just had, Can somebody tell me how to rewrite g of x so there is no longer a negative in the x moment? Yep.
Would be half raised to the x.
Yes. So in g of x, the base is really 1/2. It's not 2. It's 1/2. And the fact that this base is less than 1 tells me something special. Right? If you leave that negative in there, you might think that the base is bigger than 1. But it's really not. This negative is messing it up. So that's why we always fix that negative. Okay, let's graph both of those. Okay, I already kind of gave you a hint at what it's going to look like. So 2 to the x curves up as you go to the right. Just so I don't need parentheses, I'm just going to do 0.5 to the x. It's the same as 1/2. Hit graph. So there's 2 to the x. And you'll see 0.5 to the x coming in from the other side, curving down. If you had to describe those with a transformation, what do those functions look like? Yeah?
Or a function of the y-axis.
Yep, they're mirror images of each other. The blue is exponential growth, the red is called exponential decay, and growth and decay are mirror images. Right, so now let's look at the red and the blue one and find the domain and the range of each. Okay, let's start with the domains. So f of x is the blue one, just to make this clear. G of x is the red one. All right, let's look at the blue one. What's the domain of that graph in blue? Yeah, all real numbers. Every exponential function has a domain of all real numbers. Doesn't matter if it's a growth or a decay. It's still all real numbers. So based on what I just said, the red one is decay. The domain is also all real numbers. And I know we're specifically looking at it for 2 to the x. It would be the same answer if it was 3 to the x, 4 to the x, or 10 to the x. That would just change the steepness of the curve, but it wouldn't change the domain. Now, the range. We already did the range of the blue one earlier. We just didn't write it down. What's the range of the blue one? Yeah.
0 to infinity.
And how about the range of the red one?
Also 0 to infinity.
Yeah, they have the same range. They both come down to 0. They get close to it, but they never reach it. And they go up forever. Because they get close to it but never reach it, we're not going to use a bracket. We're going to use parentheses. Any question on describing the domain and range? So we just did it specifically for 2 to the x. Let's try to generalize it for anything to the x. 2 to the x, 3 to the x, 50 to the x. Doesn't matter. So let's look at it in general. Okay, so pretend you had some function that was a number raised to a power. If you want to pretend like it's a 2 in your head to answer this question, that will work. But it doesn't have to be a 2. It could be any number. Positive real number. Not equal to 1. So what I'm going to ask here is a set of questions about what happens as you head to the right. That's what it means if you approach infinity. And I want to know what happens as you head to the left. That means you're approaching negative infinity. So I'm going to look at my graph. In fact, I can put a copy on this page. I'm going to look at my graph, and I want to know what happens as I head to the left and to the right. let's start with the graph in blue. That's blue. Look at the graph in blue. As x gets bigger and bigger, what happens to the y value for the graph in blue? Max? It goes to infinity. As x gets bigger and bigger, so does f of x. Remember, f of x just means 1. Now, still look at the graph in blue. What happens as x gets smaller and smaller? As we continue to head to the left forever on the graph in blue. It gets smaller, and what does it approach?
It doesn't approach negative.
It approaches something.
It approaches 0.
It approaches 0.
Oh.
Yep. So, as Jalen just said, as you head further and further to the left, you are getting closer and closer to 0.
So do we ever reach it?
No,
Okay.
it's impossible to reach it.
Okay.
Now, look at the graph in red, and we're going to answer the same 2 questions. The graph in red is a decay graph. What happens as you head to the right on a decay graph? What are you getting closer and closer to? Yeah? You're getting closer and closer to 0. And what happens as you head to negative infinity? That means to the left on the red graph. Yep.
Gets closer to infinity.
Gets closer to infinity. So the point with exponentials is when you head one way, you approach infinity. When you head the other way, you approach a number. Is that number always 0? No. It depends. If you shift it up or down, you need to take that into account. But it always approaches a number one way and infinity the other. That's the pattern. So what's the difference between growth and decay? Well, when you have a growth problem, it curves up as you go to the right. And the way you can tell that something is growth is you look at the base. If the base is bigger than 1, that's growth. If the base is a decimal between 0 and 1, it'll never be negative. But if it's between 0 and 1, that is decay. And decay looks like that. That's why it's very important when you have a negative exponent to get rid of it, because the negative exponent is messing up the base. It's not really allowing you to see what it really is. So is there any question about, like, if I just gave you a problem like this, how you would identify if that's growth or decay?
Decay is between 0.
Decay is between 0 and 1, the base. So what is that one? Is that growth or decay? Yep, that's growth. How about if I did a fraction? Yep, that's growth. I didn't say fractions were decay. I said numbers between 0 and 1. That's 1.5. So that's growth. It's slower growth, but it's still growth. Any question on that? Yes.
What if the equation was for whatever reason converted over the x-axis? Would it still be growth and decay?
So you mean you had like a vertical reflection?
Yeah.
So if you had something like negative in front, we're going to talk about that. But if you put a negative in front, that would cause a vertical reflection. So instead of looking like, let me think. Instead of looking like this, it would look like that because you flipped it. I don't think that would be considered growth. No.
Would it be considered decay?
I don't think so. because growth is always going up and to the right. Decay is going down as you go to the right. When you flip it, that's really changing it completely. Well, you know what? I guess you could say that it's a growth graph that's been reflected. So you could still call it growth, but you would have to say it's been reflected.
Would that be something that you could come across questions like that?
You might be asked to identify like the transformations here. We haven't done that yet. I mean, we've done it with other ones, and it's going to be the same. But yes, you should know how to identify the transformations. So yeah, now that I think about it, you could still call this growth, but you have to say it's been reflected. Because most people, when you say growth, they're going to think this. They're not going to think this bottom one. But if you say it's been reflected, then they would know. So yeah, I guess you could still call it that. I have to think about that. All right, so now it's exactly what I just talked about, transformations. I'll write it down, and we'll identify what each letter does. Okay, so here would be your base. And there's the 4 spots where you could see transformations. This would be A, B, C, and D. Let's start with inside the function. So in this case, well, we talked about square roots. Inside meant in the root. In this case, inside means in the exponent. As close to the x as you can be. That's inside. So this whole part is inside. Start with A. A is adding or subtracting inside. So what kind of transformation would A do? What kind of transformation would A be? Yep.
Be a horizontal shift.
Yep, it's your horizontal shift. Okay, we've written it enough times now. I'm not going to write it this time, but positive would move you to the left and negative, right. B. B is still inside the exponent, but it's multiplication. So what kind of transformation is that?
Horizontal stretch.
Yep, still horizontal, because it's inside, but it's multiplication, so it's a stretch. And C and D, now we're on the outside. We're as far away from x as we can be. So C, multiplication on the outside. Yeah.
Vertical stretch.
Vertical because it's on the outside. Stretch because it's a multiplication. And the last one, D. It's on the outside, but it's addition or subtraction. Yeah.
Vertical shift.
That's your vertical shift. Remember, with vertical, positive is up, negative is down. Nothing reversed about it. Let's see, what if B was a negative? What would that do to my graph? Yeah.
Wait, if C was a negative?
B.
B? Oh, it would reflect it over the... Wait, what's horizontal? X axis? No, wait, would it be Y?
Y. I usually just say it in terms of what the B is. B is horizontal. So if B is negative, it's a horizontal flip. You could just say horizontal flip. If you want to say it over an axis, then you kind of got to think about it. Reflecting horizontally does mean over the Y. What about C? What if C was negative? Yeah?
Then it would be a x or vertical reflection.
Yeah, it would be a vertical reflection. Which vertical means it would be over the x. So you could have 6 transformations, just like we could with square roots. 2 shifts, 2 stretches, 2 flips. But they work exactly the same way. Alright, so let's try this one. It doesn't matter what the base is. The base is just the base in the problem. It has no effect on the transformations. You would always be comparing two functions, like f of x and g of x, with the same base. You'd never compare something that has like a 3 to the x to something with like a 4 to the x. Now you're comparing two different things. You always have to compare with the same base. Okay, so list the transformations needed. First thing I like to figure out is how many transformations do you think we have there? Yeah. Yes.
5.
5. Can you tell me the numbers I'm going to look at?
So positive 2.
So this positive
Or do you
2.
want it in order? I was just
No.
Okay.
That does one thing.
Yeah.
We'll talk about what that does in a minute.
And then the x itself inside the problem.
So the x here is just the same as the x here.
Well, like before the x.
So they both have 1s before the x's. So in this case, the b value is just a 1, and it's the same in both, so there's no transformation there.
Okay, the plus 1.
The plus 1, that's definitely a transformation, so there's 2.
The 5 and the negative. Like separate.
So what do you think the negative does separate?
Oh. No, it's not a reflection. Sorry.
It's not a reflection, because this is a plus or minus, which is a shift.
Yeah.
If it was a negative like that, then I would say, okay, now we have 4. But without that negative, we have 3. Okay, so three transformations. Now I want them in order. Okay, if you're not sure what the order is, look at the A, B, C, D, and that's the order. Horizontal shift, horizontal stretch, vertical stretch, vertical shift. So what would be the first one? Yeah.
You'd shift it left by 1 unit.
So shift left 1. So that takes care of the plus 1. We already said there's no b value that's different. It's a 1 here, it's a 1 there. So we don't have to worry about b. So we move on to c. Can anybody tell me what the c value is going to do? All right.
Vertical stretch by factor 2.
Good. So vertical stretch by factor of 2. And the last thing I need is the minus 5. That's the minus 5. Yeah.
The vertical shift down.
Vertical shift down 5. So you could just say shift down 5 if you want. And that covers what you would have to do with a transformation. Any questions on that? I'm not too worried about that right now. That's not important. Okay, so the last thing we're going to look at are some formulas. So there are a couple formulas we're going to look at for growth, and a couple we're going to look at for decay. So the first formula that I'm going to give you has to do with a population increasing at a constant rate. If somebody said to you, the population of that town is going up 2% every year, that is exponential. If you get a 5% raise every year, that's exponential. Anything that increases by a percent is exponential. Now, on the other hand, if you got a $1,000 raise every year, that is not exponential. That is linear. You're just doing plus 1,000 every year. So if I had a choice of having an increase in salary by percentage or by just adding a number that's just like a bonus. But increasing by percent is exponential. And the formula for something increasing exponentially involves 3 letters, P, R, and T. P is a start value. It could be a starting salary, could be a starting population, could be an initial amount of bacteria, but it's a value that you start with. R is the rate of increase, but it has to be as a decimal. for example, 12%, you'd want to put 0.12. And t, well, I didn't label it, but does anybody have a guess what t is? Yeah, it's time. So if we said, for example, bacteria in a petri dish is increasing at a rate of 10% every hour, well, t would be the number of hours that have gone by. If I said to you, how much bacteria are we going to have after a day? Well, you plug in 24 for t. It's the number of hours that have gone by. So that's the exponential growth formula. If we change one thing in that, it becomes decay. Anyone think they see what you would change there to turn it from growth to decay? Yeah?
Would you subtract r instead?
You would subtract r. P, the r, and the t all stand for the same thing. Now, you know something is a decay problem if they use a word like the population of the town is decreasing by 5% every year. The amount of acres of forest is decreasing by 2% every year. Something decreasing is decay. Increasing is growth. Now, what makes these a little bit tricky to solve is they have variables in the exponent. So we're going to use the graphing calculator to help us solve these. Everybody have those 2 formulas? So there's no question there yet. That's just a formula. We're going to do a population question right now. So in our town, we're starting with 50,000 people, and it's increasing at a rate of 2.5%. First of all, what in that problem tells you that it's exponential? I'm not worried if it's growth or decay. There's another word that tells me that. But what in that problem tells me this is about an exponential situation? Yeah.
2.5%.
Right. We have something increasing by the same percent every year. That is exponential. Now, the fact that it says increasing is growth. So we know our formula is P times 1 plus R to the T. So what we want to do is set up an equation using the formula I just said, plugging in these numbers. And then the second question is basically asking how long for the population to double. That's what they want to know. We're starting at 50,000. When will you get 100,000? When does it double? So let's start with that. Let's model this with an equation. So I try to pick a letter that would make sense. I think population would make sense in that problem, so P, or population as a function of time. Or if you don't like P, because actually we are using P in another spot, I guess you could use A for the amount of people as a function of time. P would be fine, as long as you understand where you're plugging in different letters. What's the first thing that's going to come after the equal sign? Max?
The initial amount of 50,000.
Yep, the initial amount, which is 50,000. Times. And what's going to go inside parentheses, yeah?
1 plus 0.025.
So we're going to do 1 plus 0.025, because that's my rate as a decimal. So let's just put 1.025. And I need one more thing there to finish that formula. That's the last thing that's missing. Okay. The time. So that's raised to the power of t. So there's your formula. That's the first part. So any questions on how we set up our formula? Now, there's two types of questions I could ask you with that formula. I could either say, tell me what the population will be 10 years from now. Or I could say, here's a population. You tell me how long it's going to take to reach that population. So we have to make sure you know what letter you're plugging in for. On the test, it could be either one. The question in this one is, when will the population hit 100,000? So where would this 100,000 get plugged in? Is 100,000 a time, or is 100,000 an amount? Yeah,
It's the amount.
it's an amount. So we're going to change that left-hand side to 100,000. We want to know when 100,000 equals 50,000 times 1.025 to the t. And at this point, I'm going to use the calculator to figure it out. If I'm going to use the calculator to figure out where the left side equals the right side, what do you think I'm going to do? And then what am I going to look for? Yeah?
You're going to graph a line, or just a flat line at 100,000, and then graph the right side of the graph and figure out where they intersect.
Yeah, we're going to find where they intersect. Now, since we're going to graph a flat line at 100,000, we're going to have to set the y max to at least, I would say, maybe 110,000. So put 100,000 in y1. Put 50,000 times 1.025, and you have to use x. X is always the independent variable. We can't use t. Yep.
If you wanted, could you divide both sides by 3,000 and just found when 2 is equal to 1.025 t?
Yes. Yep. You could divide it both sides by 50,000. Okay, so I got the left side in y1. I got the right side in y2. I'm going to set my window. X is time. What's the smallest amount of time that could go by? Even less. Yeah. 0. 0 would mean that that means like I'm starting with 50,000 people right now, and I want you to tell me what the population is right now. No time has gone by yet. Still 50,000. So no time. How much time is it going to take to reach 100,000? I don't know. I'm going to guess that it happens within 30 years. If it doesn't, I won't see the intersection on the screen. Y is population. Population is growing. And it's starting at what number? Yeah. It's starting at 50,000. So there's no reason for me to look below 50,000. It's going to curve up from there. And let's see. Y max. You got to go at least up to 100,000. I would go just over it. Let's do 125. Okay, so there's my line at 100,000. There's my population growing. I think I'm going to get it. Maybe? Yeah, I'm good. Okay, so just barely. If it didn't cross and it went off the screen, I would have just made X max a little bigger. So you can see it just starting to curve. And then second calc, find the intersect. So, how long is it going to take for the population to hit 100,000? Yes?
28 years.
About 28.07 years. Now, if you took 28.07 and you filled it in for time, you should get 100,000. Or you might get like 99,999 because we round. Okay. Question on that one? So when you graph something, just be careful about whether or not you include negatives in the window, because a lot of times negatives don't make sense. Negative time, negative population, that it doesn't make sense. Right? So we kind of handled that in the last one. I'm going to think about this formula again for a second. And I want to look at it for a very specific value of R. We did it last time for, what was it, 2.5%? That was just kind of a random number. But there's a number that comes up for R quite a bit that's not random. And it has to do with double. Something doubling. What do you think the percent is if something is doubling? You gotta be careful. Definitely? It's 100%. If I said to you, I'm going to give you a 100% increase on your salary, that means it's doubling. What would 100% be as a decimal? 1. So when you have the case specifically where something is doubling, your formula becomes, oh yeah, that's the initial. So I'll use the letters I did before. The initial amount times 1 plus r to the t. When something is doubling, r is 1. So now, it's the initial amount, and what would be in the parentheses? 2. That's the formula specifically for something doubling. I think I have that written down right there. So it's a 2 as the base, and the 2 is coming from the fact that you did 1 plus r, and r is 100% when you double. Now, there's something here that some people might be wondering, what's going on with that? So the exponent is t, like it was before, but it's divided by the length of time to double. This is why. What I just put a box around, right there, t divided by the length of the time to double, that has to be the number of doubling cycles. It's the number of times that something has doubled. So if I said to you, we have something like, say, bacteria, and it doubles every 8 hours. If something doubles every 8 hours, how many times will it double in a day? It's not 8. We can't put an 8 as this exponent, because 8 would mean it's doubling 8 times. If something doubles every 8 hours, how many times would it double in a full day? Yeah? How many? 3. That's why if you take how much time has gone by, I said a day, so that's 24 hours, and divide by the length of the time to double, 24 divided by 8 will give you 3, and that's what this exponent needs to be, the number of times it doubled, not necessarily the number of hours that have gone by. Now, if something doubles every hour, then fine. If 5 hours have gone by, doubles 5 times. 7 hours, 7 times. But that's only if it doubled every hour. So let's look at this one. So we have 100 bacteria, and in this case, it is doubling every hour. So if 7 hours have gone by, it will have doubled 7 times. We're starting with 100,000. I want to know when I'm going to hit 350. Okay. Doubling tells me 2 things. 1, it tells me it's exponential growth. If something's doubling, it's getting bigger. The other thing it tells me is the growth rate. When something is doubling, that is a growth rate of 100%. So the formula that we're going to use, it's really the same formula we used before. It's 1 plus r. But r is 1 because it's a 100% growth. That's why we use 2 as the base. 1 plus 1 gives me the 2. So let's set up our formula. What's the first thing that would come after the equal sign? Yeah. 100. That's the initial amount. Times 1 plus r, but we're doubling, so my growth rate is a 1. So it's just 1 plus 1, which means what? 2. And then we're going to raise that to the what power? R? T. Now it's just a matter of looking at the 350,000 and ask yourself 2 questions. Is 350,000 a time, or is 350,000 an amount? If it's a time, put it here. If it's an amount, put it here. Which one is it? It's an amount. Okay, it's an amount. So the 350,000 is going to go here, and we're going to do the same thing we did in the last problem. So 350,000 on the left. You can't multiply 100 times 2 and say 200. You don't do that. Just leave it like that. So it's 100 times 2 to the t. Okay, let's put it in. 350,000. Initial amount is 100 times 2. Yeah, so it's pretty quick to type in because I just modified what we already had. I just changed the numbers a little bit. And on my window, what should I set my Ymax to? Okay.
Like somewhat over 350,000.
Yeah, so I would say, I don't know, we could just change that to 400,000. Y min, I would go below 50,000. I would set it to the start value because we know that's as low as it's going to go. And X max, well, 30 hours, I think is probably a good X max because that's going to mean it has doubled 30 times. If you double the number 130 times, I think it's going to be way over 350,000. You could probably set this to like 20 even instead of 30. So I think it's going to cross pretty early on in our graph. Yeah. So we were way over. But that's fine. We set it more than we needed, but we can see when it hits 100,000. So second calc intersect. If you start with 100 bacteria, it's going to take just under 12 hours, if it doubles every hour, to hit 350,000. So 11.77. And that's hours. Any question on how we did that? So the last one is going to be the opposite of double. What's the opposite of double? Yeah? Halving. And that's called half. So if you look up online, like certain radioactive materials, they have what's called a half-life. And a half-life means it's the amount of time it takes for half of that nuclear material to break down and disappear and basically be safe. For uranium, which is something that's radioactive, if you look it up, I think the most common form of uranium has a half-life. Actually, I'll double check it after. It's either 4.6 million or billion years. I can't remember which one. But either way, it's a very long time. So that means if we create 100 pounds of radioactive uranium that's poisonous today, 4.6 million years from now, we'll only have 50 pounds. But it's going to take a very long time for it to go and break down and be safe. That's why when they have a problem with like a nuclear power plant, it can take I mean, that's, millions of years for uranium. Not everything takes millions of years, but it can still take hundreds or thousands of years for it to be safe to go back in that area. Depends what kind of nuclear material it was. So it's the amount of time it takes for half of a substance to decay. Notice, since it's half, it's never really gone. Like if you start with 80, let's say something decayed by half every hour. Well, after an hour, you go from 80 to 40. After another hour, you go down to 20, and then 10, and then 5, and then 2.5. You just keep taking half of it. It's never really gone completely. But eventually, there's so little left that it's no longer harmful. That's the point. And the formula for exponential decay is almost the same as growth with one change. Instead of the base being a 2 for doubling, it's a half for half. A lot of medications work that way too. So if you take a certain medication, like say 10 milligrams of something, it may have a half-life of 10 hours. So that means after 10 hours, half that medication that you took is out of your system. And after another 10 hours, half of that is out of your system. So that's another example where you might see something about half-life. So let's try this one. It says that we have a radioactive substance with a half-life of 20 days, and we're starting out with 5 grams. Let's just write a formula for it. Start with that. What's my initial amount in this case? 5? We have 5 grams. And I know to use 1/2 because it says half-life. Whenever you do a half-life problem, the base is always 1/2. The exponent is always going to be t, but I have to divide by the length of the half-life. In this case, the length of the half-life is not 1. What is it? 20. This exponent needs to be the number of times it should be cut in half. So after 20 days, the exponent should be a 1. After 40 days, it should be a 2, meaning it will have cut itself in half twice. But that's your formula. Okay, so find an algebraic representation. All right, we did that. And then let's graph it. Right, so 5 times 1/2 to the t over 20. Okay, so this is how you can type it in if you want to use the fraction. 5, put the fraction in parentheses, and put your exponent in parentheses as well. I don't know if you need to do that. You could try it without it. Probably would work without it.
I don't do the half as 0.5.
You could also do the half as 0.5. So I showed you how to do it earlier as 0.5. Now I'm just showing you how to do it as a fraction. 0.5 would be easier. Okay. So we're starting with 5 grams. And all that's going to happen is what we have is going to decay. So are we ever going to have more than 5? No. 5 is the maximum. So I would set the max at 5. And if you keep taking half of 5, what number do you get closer and closer to? But you never really reach this number. Yeah?
0.
Right. You're going to get closer to 0. We saw that earlier when we did the decay, when we looked at the range. So it's going to decay to 0. The amount of time that's going to go by, well, think of how many times do you have to cut 5 in half? Or wait, is 5 our initial amount?
Yeah.
Oh, okay. We don't know what we're decaying to. I think they're going to want to know when it's less than 1. I'll scroll down in a minute. So think of how many times you'd have to cut 5 in half before it's less than 1. Well, if you do it once, you get 2.5. If you cut that in half, you get 1.25. So I think it's going to have to be cut in half somewhere between 2 and 3 times before you get down to 1. Let's see. So there's our substance decaying. We're starting to see the curve. And it's getting closer and closer and closer to having nothing left. And the question is, when is there less than 1 gram? Well, it's going to be the same way we did the doubling problem. Put a line at 1 so you can see it. I want to know when I am under 1 gram. So what do you think I have to calculate there? What?
Wouldn't it be that you calculate the intersection and then you would write this like an inequality?
Right, we have to write this answer as an inequality. Right, so there's the intersection. It's going to take 46.4 days to hit exactly 1 gram. So when will I be under 1 gram? Using this as my reference point. Yep.
When you're less than 46.4.
Well, if I'm under that amount of days, I won't have done as much decay. Like if you say less than 46 days, so an example of less than that would be 10 days. If only 10 days have gone by, I'm still going to have this much left. This is the minimum amount of days you have to decay to get to 1 gram. So you could decay that many days or, yep.
Or you'd have to decay more, like any amount more.
Any amount more than that. Because if you decay less than 46 days, you're still up in this area. If you decay more than 46 days, now you're down under 1 gram. Does that make sense? Okay, so the time here is, when will we have less than 1 gram? When the time is greater than 46.4 days.
What did you plug into the calculator for your values to get that?
That's what I plugged in for my Y1 and Y2.
Alright, so you just put in the location. The one.
Yep. Questions on that? Okay, so let me put that up. So that's the homework for tonight. And I'm going to pause it, and I'm going to add the topics that are going to be on the test for tomorrow. Or no, for Friday.
How are you?